So last week we did two techniques, right? One was we talked about logistic regression and then generalized families. And then the next one was we talked about the k-nearest neighbor. So these are two different techniques that you can use in either when we talk about the regression or the classification context. Now, what we do is we'll look at yet another one that we already talked about, just or mentioned briefly. That's the idea of support vector machines. And if you recall, what we had said about it is that if you think about just points and you think right now a classification problem and a classification problem, let's say where you can actually separate them by a hyperplane, so some separable data set, then the idea was if we're just right now talking about a hyperplane that separates it, then which of the hyperplanes should we pick? Well, we should pick one that is kind of robust to small changes. And that was the idea of this margin. We should pick one such that there's as much space to the left and to the right as possible, given all the possible directions. And so this is what we'll do, what we'll make a little bit more precise what that means. And we are not just talking about support vector machines. Actually, the second nice or important topic is that we'll talk about that very often we can formulate one and the same optimization problems in many ways. In particular, we talk about some concept of duality today that doesn't just apply to this particular problem, but can also be used for other problems. And that will lead us to a different formulation of the problem, some different function that we need to optimize. And in particular, we'll see that in this particular way to formulate things, the data only appears in a very peculiar form. It's what's called a kernel. It's just xt times x. And so that then next time will lead us to the idea of kernels or kernelized formulations, and we'll see that that will give rise to some nice generalization itself. Okay, so we start with support vector machines, and as a motivation, let us just reformulate once more least squares and logistic regression and see how we can write it in a slightly different form. And that will then immediately give rise to that formulation here. So if we look at least squares, and let me look at least squares right now without the regularization term, just to make it simple, then what we had is we looked at, we need to minimize that cost function. I don't write even the minimum, but we need to write or minimize the cost function of that form. Okay, so that's what we had to minimize. And if we have regularization, then we have some extra terms on the right. If we're looking at logistic regression, then we had to minimize something of that form, log 1 plus e to the x n t w minus the y n x n t w. Okay, so these were the two cost functions that we had. And again, this was, of course, the sum. Now, in these examples here, right, we were thinking typically of the y's between 0. So typically here, we thought of the y's here to take on values let me just write here y tilde, and you will see in a second. So typically, we thought about that the values were taking, or that the y-ns were taking values in 0, 1. It will be slightly more convenient right now, and it's, of course, a trivial change to think of values in plus minus 1. So yes, please.
Please can you turn on the lights?
Better? Okay, thank you. And so to do y plus minus 1, it's of course a trivial change. And so let's think of us, there's of course two possible mappings. Let's think right now that this goes to minus 1 and 1 stays 1. And we can write this map. And so now let me then call this yn, and this is why I call this tilde. And so then what we have is that then the y is just equal to 2 to the y tilde n minus 1, right? If this is 0, then I have 2 times 0 gets to minus 1. 0 goes to minus 1. If this is 1, then 2 times 1 is 2, minus 1 is 1, and this goes to 1. Okay, so I'm just thinking of this map here. And so now, let me just rewrite this. Okay, so now we just rewrite it in these coordinates here. And also, since we're thinking of the minimization here, it's not important that even the W has to be the same W. So for example, for the least squares, let me think of the W. So let me write here also W tilde. But let me use here W. So it will turn out that they are not exactly the same parameters. They're in one-to-one relationship. And I just want W here to be equal to 2W tilde minus E0. I'll tell you in a second what that means. And W tilde, so then I have just W over 2 plus a half E0. So what I assume here is the following. I assume that as typically that the constant term is x0 and it's 1. So we have the constant in there. Okay, so I don't need to augment it. I have shown every vector, data vector, has the constant in term in there, and that's the term 0. And then this is just a unit vector at 0. Okay, so all this means is that basically these two vectors are just scaled by a factor 2, but at the component 0, there's an extra constant of a half in there. Okay, it's just a trivial map between. And so if you then write it down like this, okay, if you just play around a little bit, you will see that this can then be written like this. If we're thinking of 4 times this one, will then be equal to that, will be equal to 1 minus yn x and t w squared. Okay, just an identity. So the only thing that changed is that so you remember this was between 0 and 1, and this was plus minus 1. So these ones are plus minus 1. So let me first write it in this form. You first see that this is identical to this form. Okay, and now if I have a yn which is just plus minus 1, that's exactly the same as writing here a 1 and then writing here the yn here. Okay, so minimizing the left or minimizing the right, I might get a different w because they're related by these things, but it's exactly the same problem. Okay, and so let me write this down now in the following form. So this is sum n is 1 to n, and so let me let me write this as mean squared. I think in the note I write it at least instead of least squared as mean squared error. And so this depends on two things, namely the x and t w and the yn. And this function here, mean squared error, is a function of two things and has exactly this form 1 minus y z squared. Okay, it's just a cost function. And so the cost function is this. This is basically your prediction that you're making based on the data, right? And this is the sign that he's saying, is it plus or minus 1? And then the cost function is just this, okay? 1 minus. All this means is that the prediction, of course, is relative to the label, right? Whether the prediction is plus or minus has to do with, if this is correct or not, has to do with the label is plus or minus. So you can think of the y times this prediction as being kind of the normalized prediction, meaning positive is correct, negative is incorrect. Okay? And so we can do the same thing here. This is for the least squares. If we do the same thing here, we can see that you can write this. You don't need that formulation. Okay, so there's nothing changing here, but you still need the plus and minus 1. You can write it like this. And what do I have here? I have log of 1 plus e to the minus yn x and t w. Okay, so that's the same formulation. So this is the same thing as this, the claim. So again, here the y is plus minus 1. Here the y is 0 and 1. And that's easily checked. You just have to check what happens with it 0 or 1. So let's just check 1. So let's assume the yn is 0, right? Then all I have is the log of 1 plus e to the thing here, right? Y is 0, or the y tilde is 0, corresponds to the y being, let's see, corresponds to the y being minus 1 here, right? And so now if you look at this, this is log 1 plus the y is minus 1. There's a minus. This gives me a plus. And this is just x and tw, right? So you have identity between the two. And if the y and tilde is 1, right, then the y is also 1. Then what you have here, if this is 1, then you simply have here minus this term here, right? But what is this term here? Well, if you have minus this term here, that's also the same as log of e to the thing here, right? And if you put that together in here, then you will see that there's simply one term with a minus that comes here. This one will cancel and become 1, and this one will become e to the minus x and t, and that's exactly what you have here. Okay, so it's again identity between the two. We have just rewritten it. So let me write this now as n is 1 to n, and let me call it the logistic loss. And so again, this depends on two parameters, namely x and t, the prediction, and then the actual label. Okay, and so here the logistic loss is just log of 1 plus e to the minus y z. Okay, so the only point of rewriting is that I write the two kind of in the same form as a loss function, right? And then we can compare the loss functions, and that will lead us to the third loss function, which will be exactly the loss function of the support vector machine. So for least squares, we're using that loss function, right? Just the square of this kind of normalized prediction that we have. For the logistic regression, we're using the logistic loss function, which is the log of 1 to e to the minus this normalized prediction, right? And so now let us introduce a third one and then discuss what the differences are. And this third one will be exactly lead us to support vector machines. And so the third one is what's called the hinge loss. And so the hinge loss, again, of the prediction and the label, it looks at first a little bit like the mean squared one. Okay, so we're having this times z. But now this means plus, where this plus is z if z is bigger or equal than 0, and otherwise it's 0. Right, so it's just the function that takes on, it's this function, okay? Just the hinge function. So we'll see that we get support vector machines if instead of this we're using that, and we'll also need a regularizer, okay? But before we're talking about the regularizer, let us just talk about these three functions, what they do. Okay, how do they look different, and why might there be a difference in their behavior? So let us just plot. Okay, in the notes you have better pictures. So maybe that's 0. This is 1. This is 2. Okay, and so what we will plot is the loss of them for y is equal to 1. Okay, so we'll just plot that, and so we'll just see what they look like. So let's see first for the mean squared error, right? This is just a square with mean here 1, so whatever this looks like. Right, so the idea there is that in principle I want to hit the labels plus or minus 1, okay? So this one is just because we're looking at the normalized one, right? So we're always looking relative to the label. And so this one will punish any deviation. So we would like to predict the label 1, the normalized label 1. Okay, if we get it exactly, we pay no price. But any deviation, doesn't matter if it's positive or negative, will be punished, okay? We'll pay the same price and it's symmetric. And in particular, anything more positive, actually to some degree, is good, right? We are very confident, but nevertheless, we get punished for it. Is that clear? Right? Okay, so this is thing. Then the hinge loss looks a little bit different. The hinge loss is, I don't know now, whatever, if it's lower, higher thing, it doesn't matter. But it looks like this. Sorry, the hinge loss, the logistic loss. So this is what the logistic loss looks like. Okay, so here's the following. In logistic loss, remember, more positive is good. Okay, so you're confident about your prediction, it's correct. Okay, once you're on this thing, this is bad. So it does kind of the right thing in that it punishes more when you're wrong, right? But you always get, there's just some continuous thing, you get, the more you're right, kind of, the more you're on the right-hand side and you get confident about your prediction. Think of very large being very confident about your prediction. On the left, being wrong, okay, also very confident, but unfortunately wrong, okay? So it does the right thing, that if you are wrong and, very on the wrong side, you get punished more, but you always will have some punishment, okay, and this goes down somehow smoothly. Okay, clear? But it is asymmetric, so it's better than this mean squared error around when we're thinking around here. Okay, it doesn't do that stuff that it punishes equally deviations that are positive than deviations that are negative. So it's better and more meaningful. And so now, what does the hinge loss look like? Well, the hinge loss looks like this. Okay, so look, this value here, right? So remember, this is relative to the predicted value. So it's linear when it's less than 1, and it's 0 above. Now, it's not, so there's no punishment once you have a prediction that's 1 or above, okay? But there's linear punishment below. Now, note that this inflection point here is not 0. So it's not like that when it's just negative, when it gives the wrong prediction, it gives you an error, okay? And just when it's positive, it gives you no error. This is shifted a little bit to 1. So you still pay a cost as long as your prediction has the right sign, but it's not very confident about this, right? So you just have up to 1. It tries to push you that when you give a prediction, that you give a very confident prediction, right? 2, 3, okay? Then you pay nothing. But as long as your prediction is less than 1, yes, you have the right sign, right? But you still have to pay for it. And that exactly will lead us to this idea of margin. So this is exactly what will define these margins here. It will try to find something that pushes things as far as possible so that you don't pay anymore. Make sense? Okay, so this plus the cost function will now give rise to support vector machines. Okay, so let's see. I guess we have. So, okay, so let us first maybe write down the formulation. So, and then we can discuss. So again, you want to minimize over all W, right? And then it's what you want to minimize, exactly this hinge loss. And then we still have a regularization term. Okay, so what we want to minimize is this cost function. And so maybe let us talk a little bit about what this will do. Okay, so let us look at something that is maybe linearly separable. So we have some data in your notes. You have some nice plots in there. So we're just representing things in R2, and we have two particular data things. Okay, so these are the zeros and the ones, or the plus and minus ones. We need to separate them. And so, and what we want to do is, right, our prediction is again based on some linear function, so it's just a hyperplane here. So the question is now, what kind of hyperplane should we pick? Right, so we have many choices that separate out, perhaps. Maybe we should pick this hyperplane, or maybe it's better to pick this hyperplane. And so the question is, what is it that we should pick? Okay, so if we first look at maybe data that is, if you look in your notes, that is not even necessarily separable, just to introduce some notation. I don't know, maybe something like this. Then you will see whatever we get the hyperplane by support vector machine. And what you will see is around it is, I guess in the notes, it's some kind of pink region. I don't know what it looks like, maybe like this. Okay, so what is this region? This is exactly the margin here. This region is exactly something that's parallel. These are given by two hyperplanes that are parallel to the main hyperplane. So that's the hyperplane that makes the prediction. And the margin is exactly these two hyperplanes here. And how are these two hyperplanes defined? They're defined that once you give me the W, so once you give me what is the direction, this defines, of course, the hyperplane, right? Remember, the W is just a vector that's perpendicular to the hyperplane, right? So this W defines the hyperplane here. But there are two things, right? So there are many W's that might, and remember again, the constant is in here. So we can also shift it. So we have, again, the constant. It's not just that we have the direction, also constant in here. But there are two ways, what we have. On the one hand, the W defines the hyperplane, but there are many W's which would define the hyperplane. So for example, this W defines a hyperplane, but this W would also define this hyperplane. Okay? So there's a scale still in there. And this scale is now exactly what determines the region here. Namely, what we're looking for is exactly all the points here, such that x times W, that this is smaller equal than 1. Okay, so we're looking at all the things where this product is smaller and equal to 1. Okay, so why we're looking things that's smaller equal to 1? Just look at this thing here, right? So that's the prediction, right? And so with the sign, that's just a normalized prediction, right? As long as this is smaller equal to 1, 1 minus this plus will still give us some kind of penalty, right? Will give us a loss. But as soon as this is larger than 1, right? And let's assume also the right sign. Then I have 1 minus this, right? Then this will be negative, and plus, there's no penalty. So any point that's inside here, there's still, I still have to pay some penalty. It doesn't matter if I'm on the correct side or on the wrong side, right? Clearly, if I'm on the wrong side, I pay a penalty, right? But even if I'm on the correct side, because this hinge function, hinge laws, it's 1 minus this prediction. If this prediction is less than 1, and then the plus value, so the, just the positive part of this, will still be non-negative. Clear? So the point is that whatever you give me as a W, this defines a region, right? The region where all the set of points such that this is smaller or equal than 1. Any point that is either on the wrong side of this prediction, right? This is the side that gives me the prediction, right? So for example, this side, let's say, predicts zeros here, or or circles, right? So if I'm here, I don't incur any cost because I'm outside this margin, right? Here also, I'm just outside the margin. If let's say, if I'm here, then incurring cost, I'm wrong, right? And I get certainly some cost function. It's just linear by how much I'm wrong, okay? But even here, I incur a cost because I'm on the right side, but I'm not quite yet confident enough, right? So the confidence here, I'm just thinking of this normalized value, the prediction times the label, right? And as long as this is less than 1, I'm still kind of like, yeah, okay, but I'm not sure enough, and so I still get a penalty. Make sense? So, okay, so this is the margin, okay? So the margin is determined essentially by the scaling of this. So how wide, so in terms of, if I'm looking at the norm, if I'm looking at the norm of W, okay, then in terms of the norm of W, how wide will this be? The width, how wide is that? What's the width if I measured that? Doesn't depend, doesn't depend on dimension because I can always project it. So if I make the W larger, will this margin become larger or will it become small? Let's assume I draw you a picture. Now I take the same W but multiply it by 2. What will happen to this picture? Loud? You have to be confidence above 1, otherwise I don't hear it. Well, just think of scalar, right? So I take W times X must be less than 1, right? The X gives me the dimension. If the W becomes twice as large, then the X will become half, okay? So this means this width here, right, is 2 to the size of W, right? Right, because I have twice the size. I go from I have plus 1 and minus 1, right? So it's twice this, and it's 1 over the norm of the W, right? So, okay, so now let's look at this cost function here, right? On the one hand, yes, please. Well, we want to find this thing that minimizes, right? So there are two terms. It's this. That's what I was talking about. That's a penalty, a cost, a loss. Okay. It's not about the prediction. It's not about the prediction. The prediction will be correct. Okay. It's how do you get the prediction? The prediction means this is the formulation of how you find the predictor. How do you find the W? This is not the prediction. That's the cost function that gives us the hyperplane that we then use. As always, we always have the two things. We have the actual predictor, okay? In this case, they're all linear, okay? In some sense, they all give us some hyperplanes at the end. But which hyperplane we pick has to do with the cost function that we pick, right? And so the least square and the logistic and this correspond to different optimization problems. And so in general, they will give us different hyperplanes. Okay, so here we're talking about how do we find the hyperplane that we want to use? Once we have the hyperplane, the prediction is trivial. I just go plus minus 1, then I don't charge you if you're wrong. Okay, whatever. Okay, you can then you can decide how you want to assess it in any way you want. Okay, this is just how we right now think about optimizing things. Okay, good. So now, okay, so this is the width, right? So again, this cost function has two parts. It has this part, which we just talked about. So depending on how I choose this, there will be a different number of points that are, depending on what I choose here in the W and the scaling, this will change, right? And the orientation will change. And so this means there will be different numbers or different numbers of such points in there, right? And so the cost of this one will change, right? That's one thing. And second of all, depending if whatever the W is, I also get charged with the magnitude for the W, right? I get charged for the magnitude squared. So I pay, so I want to use in principle I want to use small w's, right? Because if I have small w's, then the right-hand side doesn't matter too much, right? And then I don't pay much for the right-hand side. And what I at the end of the optimization is the sum of these 2 points, right? Make sense? So let's first assume that let's just think about it, that let's say the lambda is small, okay? Now, we don't make it precise exactly what it means, but so what it means is that really to first order, we are interested in minimizing this thing here, right? So if the lambda is sufficiently small, what really will matter is, if think now of this one case here, right? What will matter is that I pick first of all, I pick a hyperplane that really, if this is separable data, that really separates it, right? That will be the first thing I want to do, right? And second of all, I would like to pick the margin, right, in such a way, whatever it is, I want to pick the margin in such a way that I don't include any of this, whatever. Let's assume that's the margin here. So once I pick that as the plane, the hyperplane, and then I pick the scaling in such a way that there's no point in there, right, then it means that I can make this part here to be 0. Because there's no point in the margins. If I have separable data, then there is by definition means there's a hyperplane that I can draw such that everything, on the left that should be on the left is on the left, everything should be on the right is on the right, right? And then once it is, then there's always some kind of gap between them, right? And now I can pick the margin so that no of the point will be in there, right? If I do this, then I can make this cost function to be 0, and this will be the major part because we assume that the lambda is small, okay? Nevertheless, let's assume I have that. For any particular one that I have here, right, how should I pick the W such that, so let's assume I give you the direction already, right? But you can maybe still shift things, and you can still decide on the scaling of this thing, so that you can still see how far, how should I scale the W. So how should I pick the W?
So as soon as you separated the 2 classes, you should pick the W like the smallest one because you want to minimize. And when you pick the smallest one, you maximize the margins.
Exactly. So this means, okay, so in general, right? So what I want is I want the W as small as possible. So let's assume I give you already some particular direction. Let's assume it's this one, right? Then I can still decide on what the scaling of this thing should be here. So I want to make the W as small as possible. So I start with some scaling maybe here, right? I have a particular cost because this cost will, this will correspond to some W. But, I can still make this W a little bit, smaller, right? And then this will make this larger here, right? And then this will make the cost here smaller. And I still don't pay any penalty here because none of this is in there. So clearly I will do this until it just hits, right? So ideally I should pick this in the center of this and I should enlarge it such that exactly at some point there will be a point here and at least one point here and one point here that touches it, right? If I now went further, I would start incurring a cost here, right? And assuming the lambda is small enough, this is the more important. So suddenly this would terminate, right? This would be the determinant cost here. And so clearly I should pick then this such that I have exactly these kind of witnesses here. I cannot make it any larger, right? So this will mean for any direction, clearly I should branch it out. But it will also mean that if I now go over all possible directions, right, I should pick that direction for which I can make the margin as large as possible, right? Because all the directions that are separating have cost here 0 anyway. And the only thing that matters is how large can I make the margin, because then I can make the W as small as possible, okay? And that's why people say, support vector machines, you basically maximize the margins, okay? Now, of course, you have to, when you then have data, something like this, you still pay something, okay? It's no longer such a clean picture, but I think it's still a good picture in general to keep in mind. Okay, so the cleanest one is think of separable data, think of this lambda being small, and then it's a fairly clear picture, I think, what this thing should do. Any questions? Okay, so in principle, right? In principle, we are done with support vector machines now. Okay, now we just have to ask about how can we still do the optimization. And in principle, it's easy because, right, if we're looking at that, then this is anyway just some, so this is, you know, this function looks like this, we said, right? This function here, so this is convex here. The other function is convex, right? So this will be a convex function in W. Now, okay, we have a small problem that this is not differentiable here, but we already all have mastered that problem, right? So there will still be subgradients here, right? So we can still define something like a derivative called the subgradients here. And so we can just use the stochastic gradient descent. So the problem is convex. It has subgradients. So basically it has, up to this one point, it has derivative. And so this means we can just use stochastic gradient descent. Right? And so in principle, we are done. So what we want to do now is to reformulate it. Okay, so this would be one way to do it, and indeed, this might be the right way to do it depending on what the parameters is. But what we want to do is now we want to reformulate this problem in a slightly different way. Will lead us to a different way of an optimization problem. And this will lead us to an idea of kernels, and it will also lead to an idea of a different optimization that, depending on what the parameters are, might actually be more convenient to do. Okay, so we want to write this in a slightly different way. Okay. Tricky. Now, there's a general principle of how one can do this, but rather for us talking about the general principle, we do this for this very concrete example. And we'll probably see some other examples where we can do the same kind of thing. So what is the basic idea? Well, we have this function here, right? We have this whole thing that we had, this bracket, is, another way of writing is that this is just simply the zero between, the max between 0 and z, right? That's just another way of writing it. And so now, max is not a very nice operation to deal with, right? It's much nicer to deal with functions where we can just take directly derivatives and scale and so on. So one way to rewrite this is the following. We take an alpha, which is important that is between 0 and 1, and we just write it as alpha times z. And it's the max of this alpha times z. So now instead of having the function max of 0 and z, we have the function of alpha times z. Right? So that's a very nice function. But unfortunately, we still have this optimization or the maximization we have to do. Right? So if z is negative, right, then picking an alpha between, picking alpha between 0 and 1, then clearly picking alpha is 0 gives us 0. Picking any other alpha gives us a negative number. Right? So clearly, the best choice will be to pick alpha to be 0. Right? And if z is a non-negative number, right, then if we have a non-negative number, then it means that we should pick alpha to be 1, right? Because if z is, let's say, 0.3, then 1 times 0.3 is again 0.3, right? So that's fairly clear and is quite trivial. And so the idea will be now that we're using this function instead of the formulation up here, okay? So what we get is that we're dealing with nicer functions. On the other hand, we have to deal with this extra maximization that we have in here, okay? And so there's a little bit of trade-off. So let us think of, before we plug this in explicitly, let us think of the following. Let's assume we have a cost function, and we need to minimize this cost function over all w, right? So that's always what we have to do. But now let's assume that I could write the cost function. Let's assume I could write it as a maximization and over some, let's say, alpha. And then we have to specify this alpha will always be in some box 0 to 1, but let's forget this for a second, of some other function, g, and this function will depend on w and alpha. Okay? So, we haven't made it seemingly more complicated. Instead of taking our cost function that we just need to minimize, we're looking at a more complicated function, right? And now we have to, so now what will be the point, right? So now the point will be that this is, of course, the same as the min over the w, the max over the alpha of the g of w and alpha. Right? So now we can solve our original minimization problem with something seemingly more complicated, because now we don't just have the minimization, we also have the maximization inside. Yes? So, yeah, so this would mean that for any fixed w, okay, for any fixed w, there will be the maximum of the alpha gives me that function. Okay? Clear? Good. So now, obviously, we hope to gain something, because if we just make it more complicated, what's the point? Okay? So, so there are several questions that we have. So what would be a suitable GW of alpha? Right? So what, I give you a formulation. How would you pick a suitable alpha? And what does it even mean to be suitable? 2, well, the one hope we could have is the following. Perhaps this is equal to the following. Perhaps we can exchange the min with the max, right? Perhaps we can do this. So can we exchange the min with max? Under what condition is that admissible? And the third one is, when does such a thing lead to more efficient algorithm? Okay, so we'll have to see examples where at the end, when we do this, so we do the program, maybe we find a g, maybe we prove that for this g we can exchange them, and now we have to solve this other problem, and then what exactly would happen, or under what circumstances would that formulation now be better? Okay, and so we'll take a break, and when we come back, we'll answer these 3 questions.